All right, welcome everyone. Today we're diving into an explainer on a seriously counterintuitive computer science concept. We're going to break down exactly why finding a specific element in an unsorted list, a process we call selection, can actually be done in linear time, or O of n. Now, if you've ever tangled with big O notation, you already know that sometimes the raw math just doesn't quite match our initial human intuition. But stick with me because by the end of this, we're going to make perfect sense of it together.
So to really set the stage here, I want to kick things off with this exact real-world question from a super confused developer on Stack Overflow. They asked, if we do O of n work at log n levels, why isn't quick select O of n log n? And honestly, it is such a brilliant question because it points out a massive trap that so many of us fall into when analyzing algorithms. Our brains just naturally want to multiply those two terms together. But to understand why that's actually wrong, we first need to take a step back and understand the problem we're trying to solve.
Section 1, the Kossoff element problem.
Before we get into the heavy math, let's quickly define this. This is known as the selection problem. Simply put, it's the challenge of finding the kth smallest or largest element in an unsorted array of n elements. Just imagine you've got this massive, totally unsorted database of 1 million user scores, and you just want to find the 10th largest score. Or maybe you want to find the exact median. How do you actually pull that off efficiently?
Section 2, the sorting trap.
Look, the absolute most natural instinct here is to just sort the data first, right? But as we're about to see, that instinct is a complete trap. If we just sort the entire array to find our element, we hit an immediate efficiency wall. We're stuck with an O(n) log n time complexity because we're literally organizing a ton of data we just do not care about. Now, you could try using a data structure like a min heap to track the top k elements. That does improve things to O(n) log k, which is awesome for a small k. But if you're looking for the median, where k is half of n, well, you're right back to O(n) log n. We want to beat this. We need an algorithm that scales purely linearly.
Section 3, the quick select shortcut.
Enter Hoare's quick select algorithm. This is an elegant, linear time alternative invented way back in 1961. And the core difference between quick select and its famous cousin quicksort is honestly just beautiful. In quicksort, you pick a pivot element, you partition the data into smaller and larger halves, and then you have to recurse on both sides to organize the whole thing. But quick select is much smarter. Because we only care about finding one specific rank, say that 10th element, once we partition the data around a pivot, we can just throw away half the haystack entirely. We literally only recurse on the one side where our target element actually lives.
Let's break down how this actually plays out. You pick your pivot and partition the array. All the numbers smaller than the pivot go to the left and all the larger ones go to the right. After the single linear pass, that pivot element is sitting in its final, perfectly sorted position. So you just check that index. If it matches our target k, boom, you're completely done. If not, you use that pivot's position like a signpost. It tells you exactly whether you need to search the left subarray or the right subarray. We are consistently eliminating a huge chunk of the remaining array with every single recursive jump.
Section 4, why is it O of n?
Since we're eliminating half the array at each step, this brings us right to the mathematical climax of our explainer, and back to that Stack Overflow myth we started with. Our intuition is screaming at us. Binary search halves the array at each step and takes O of log n time. Quick select also halves the array at each step, meaning it has log n levels of recursion. But at each level of quick select, we are doing O of n work to actually partition the data. So shouldn't log n levels multiplied by O of n work equal O and log n? It feels so logical, but it completely misses the reality of how the math actually resolves.
Here is where the absolute magic happens. Yes, there are log n levels, but the amount of work we do at each level is not static. It shrinks dramatically. Think about it. At the first level, we partition the whole array, doing n work. But at the very next level, we've thrown half the array away, so we only do n divided by 2 work. At the next level, it's n divided by 4 work, then n divided by 8, and so on.
When we write this out as a sum of all the work we do across all the levels, we get a geometric series. It's n plus n over 2 plus n over 4, which we can easily factor out to n times the sum of 1 plus a half plus a quarter plus an eighth. And here's the wild part. Even though this series goes on infinitely, it actually converges. If you keep adding half of what's left, you never actually exceed a specific finite limit.
And that limit is simply 2n. The absolute maximum amount of work you will ever do across all those logarithmic levels, assuming you keep having the array perfectly, is just 2n. And, in big O notation, we always drop the constants. So that means our time complexity simplifies perfectly to expected O of n.
To really reinforce this mathematical revelation, I love this quote from a Stack Overflow contributor responding to that original thread. They said, when you do something and then do something else, you sum the orders, not multiply them. You aren't doing n work log n times. You're summing a rapidly decreasing amount of work over those levels.
Section 5. Median of medians. Now there is a catch here. The math we just walked through assumes we're actually splitting the array nicely in half, or at least close to it on average. But what happens if we hit the absolute worst-case scenario? If standard quick select gets incredibly unlucky and just happens to keep picking the absolute largest or smallest number as its pivot, well, we aren't throwing away half the array, we're throwing away just one single element. The work doesn't halve, it barely shrinks. N plus n minus 1 plus n minus 2. That degrades your performance down to a really painful worst-case ON squared. So to guarantee ON performance, we need a way to mathematically guarantee a balanced pivot.
It actually took a literal dream team of computer scientists to crack this worst-case scenario. This algorithm from 1973 was created by Blum, Floyd, Pratt, Rivest, and Tarjan. Just to put that into perspective for a second, 4 of these 5 researchers went on to win the Turing Award, which is basically the Nobel Prize of Computing. Their solution is nothing short of brilliant.
They invented the median of medians technique. Instead of just picking a random pivot and crossing their fingers, they proposed chunking the entire unsorted array into small groups of 5 elements. By finding the medians of these tiny groups and then recursively finding the median of those medians, they could pinpoint a pivot element that is mathematically guaranteed to be a solid, middle-of-the-pack value.
The really crucial point here is how this group of 5 method guarantees our bounds. By doing this, they could mathematically prove that at least 3n over 10 elements will always be smaller than our pivot, and at least 3n over 10 elements will always be larger. This means that literally no matter how unlucky the data layout is, we are guaranteed to eliminate a massive chunk of the array, at least 30%, with every single recursive call. Because the subproblem shrinks by a guaranteed fraction every single time, our geometric series math still holds up completely, guaranteeing a worst-case time complexity of O of n.
So, we've seen that standard quick select is expected O of n, and the absolute genius of median of medians guarantees worst-case O of n. But I want to leave you with a really fascinating question to ponder. If median of medians guarantees that worst-case linear time, why do almost all real-world programming libraries still prefer the standard randomized quick select? Well, it all comes down to the hidden reality of constant overhead. Finding all those medians takes extra operations. In practice, the sheer simplicity of randomized quick select makes it so much faster on average that we are totally willing to risk the incredibly rare O of n worst-case scenario. It really makes you wonder, what trade-offs are you making in your own code? Keep that in mind as you apply these concepts.